nuclear age, human spies are a vanishing breed. Taking their place are complex spy machines operating in the cold blackness of space. This video ordnance program takes a look at the secret world of spy planes and spy satellites. Aerial espionage is not new. The first military use of aircraft, including balloons and early biplanes, was for aerial reconnaissance. With the advent of nuclear-armed intercontinental weapons during the Cold War years of the 1950s, strategic intelligence became vital to national security. Desperate for intelligence on the highly secret Soviet programs, the United States began development of the first specialized high-altitude strategic reconnaissance aircraft, the legendary Lockheed U-2. The U-2 and its current version, the TR-1 we see here, were of very unconventional design. With their long, thin wings, they almost resembled sporting sailplanes. The long wings give the U-2 and the TR-1 the ability to fly in the thin air 15 miles above the Earth's surface. Ordinary military aircraft seldom fly over 35,000 feet, while spy planes are designed to operate at over 70,000 feet. At 70,000 feet, there's not enough air for the small wings of normal combat aircraft to give lift or to maneuver, and their jet engines would fail from lack of enough air. The U-2 and the TR-1 are powered by special jet engines that require a minimum of fuel and air to operate. The U-2 first began flying missions over the Soviet Union in 1956, photographing Soviet missile sites, bomber bases, and weapons proving grounds. These missions were vitally important to American leaders as they revealed that the alleged missile gap did not really exist. The flights were bitterly denounced by the Soviet Union as illegal. Yet, in the long run, they helped relieve tensions between the superpowers and paved the way for the first nuclear arms control talks in the early 1960s. But the U-2 was not invulnerable. By 1960, the Soviets had developed the new SA-2 guideline missile, which was capable of reaching the U-2's flight path high in the stratosphere. In May 1960, a CIA U-2, piloted by Francis Gary Powers, was shot down in the central Soviet Union by an SA-2 missile. President Eisenhower ordered U-2 flights over the Soviet Union suspended, an order which has remained in effect until today. But the value of spy planes has not disappeared. From their high perch 70,000 feet in the sky, on the very edge of space, spy planes like the U-2 and the TR-1 can fly outside a country's airspace and still be able to photograph objects dozens of miles inside their borders. Even though the Soviet Union was off limits, American spy planes still flew over other trouble spots, gathering information. The Cuban Missile Crisis of 1962 provides the best example of how a modern strategic espionage system functions. In 1962, Nikita Khrushchev decided to secretly place nuclear-armed missiles in Cuba aimed at the United States. American intelligence agencies began to get suspicious of Soviet activity in Cuba in the late summer of 1962, when these strange construction sites were photographed by U-2s flying over western Cuba. These star-shaped entrenchments were identical to SA-2 guideline missile sites seen in the Soviet Union, the same type of missile that had shot down Francis Gary Powers. It was unusual to see so modern a missile system so far outside the Soviet Union. Was it being placed in Cuba to protect an even more secret weapon system? The first hints came from a Soviet officer, Colonel Oleg Penkovsky, who was spying for Britain and the United States. Penkovsky supplied the West with manuals for 2 new nuclear-armed missiles, the R-12 and the R-14. In October 1962, U-2s flying over western Cuba took these pictures of new construction. Air Force analysts quickly realized that they resembled the launch pads shown in Penkovsky's manuals. Low-altitude missions by RF-101 spy planes brought back even more detail. They showed the launch pads and nuclear storage facilities of the missiles. It was this evidence that led President John F. Kennedy to blockade Cuba and force the Soviet Union to remove the missiles.
It shall be the policy of this nation to regard any nuclear missile.
But the value of strategic reconnaissance was not limited to the detection of the missiles. Professor William Burroughs, author of Deep Black, a highly regarded study of space surveillance, explains the value of strategic reconnaissance.
It played two roles during the Cuban Missile Crisis. The first and most obvious was spotting missiles in Cuba. The Russians, of course, had brought in ballistic missiles, and we found them. There was another role, however, which is not generally thought of in terms of the crisis, and that is the fact that both sides were watching each other in terms of preparation for what could have been World War III. In that regard, we knew that Khrushchev had been bluffing when he said that he had as many ballistic missiles as he said he had. We knew from our satellites that that was incorrect. Conversely, Khrushchev knew that Kennedy was not bluffing, that we were sending a lot of stuff down to the Caribbean, Air Force jets and Navy ships and so on. So in that regard, it probably helped to back Khrushchev down and diffuse a situation that could have led to World War III.
The vulnerability of the U-2 to Soviet missiles forced the United States to develop an even more sophisticated spy aircraft, codenamed Oxcart. The early 1960s also saw the development of the world's first spy satellite, codenamed Corona. The Oxcart program resulted in the most sophisticated spy plane ever developed, the legendary SR-71. Even today, 25 years after it first flew, the SR-71 Blackbird is remarkably futuristic. It was the first design to incorporate stealth features in order to reduce its visibility to radars. It is still the fastest jet aircraft in the world, with speeds up to Mach 4, nearly 3,000 miles an hour.
Well, it's the fastest aircraft in the world and the highest flying aircraft in the world. We hold the absolute altitude records and the absolute speed records. It holds an amazing record from New York to London, 1 hour and 55 minutes, and from Los Angeles to London in 3 hours and 54 minutes. It is without a doubt the fastest aircraft in the world.
While some other combat aircraft are capable of speeds over Mach 3 for short durations, the SR-71 is unique in that it flies at 3 times the speed of sound for nearly the whole mission. It is designed to operate at very high altitudes, where its power plants work best.
Every mission that this aircraft flies, it essentially goes to Mach 3 and 80,000 feet. F-111s are designed to fly low level. SR-71s are designed to fly high altitude and very fast. That's where the sensors perform. That's where our fuel economy is best. That's where we're designed to meet our tankers on a given profile. So basically, high altitude, high speed is what we're in business to do every mission. We don't fly any slower or lower altitude because we're not capable of performing there.
The SR-71's unique flight profile also causes unique problems. At sustained speeds of Mach 3 and greater, the outer skin of the aircraft becomes heated to over 500 degrees Fahrenheit. The canopy glass becomes so hot that the pilot cannot touch it, even with insulated gloves. The structure of the aircraft was carefully designed to permit the outer skin to expand with heat and contract when cooled down. When on the ground before flight, fuel can leak out from small gaps in the structure. But as the SR-71 builds up speed, the titanium skin of the aircraft expands, tightening up the structure for the high-speed environment.
It's just like going into a big oven, because you're creating friction on the aircraft, stretching it out, and then sealing itself together. When it's sitting on the ground, it's all cooled off. So when he comes down, he flies in the pattern, and he also cools himself off. So it kind of goes back to the shape it's in now.
Like many highly secret espionage systems, the SR-71 has had numerous code names over the years. The CIA originally called the project Oxcart, and the Air Force called it Senior Crown. It eventually became known as Blackbird due to its paint scheme. But the name, popular with many of its crew, is Habu.
It is a nickname in the SR-71 community. The Okinawans have a nighttime, venomous, and very quick snake that only comes out at night and goes back before morning. When we first started operating over there in the mid-60s, the local Ryukyans started naming us the Habu because we seemed to operate in the same parameters as the snake.
The missions flown by the SR-71 are top secret, but from historical records we can get some sense of the type of missions the SR-71 is capable of performing. A typical example took place in 1973 at the time of the October War in the Mideast, when a single SR-71 was sent in to get photos of the fighting. On October 12, 1973, an SR-71 left Griffiths Air Force Base in upstate New York and headed over the Atlantic at over Mach 3. Over the Azores, it dropped down in altitude to meet up with a KC-135 tanker to refuel. It climbed to 80,000 feet again, nearing Crete, for another aerial refueling. Its main mission was a 25-minute pass over the battlefields in the Suez Canal area, then turning to pass over the Golan Heights, where heavy fighting was taking place. With its photos secured, it then passed back out over the Mediterranean and headed for home. The entire mission covered 11,000 miles of travel and took about 10 hours to fly. Very few photos have been released by the United States Department of Defense which show the type of imagery captured by the SR-71. These publicly released photos are probably not the best quality, but provide some idea of the type of intelligence data the Habu is capable of gathering. The crew of the SR-71 consists of 2 men, located in the front section of the aircraft.
The aircraft basically has 2 crew members, a pilot and an RSO, Reconnaissance Systems Officer. I'm a pilot, and my duties as a pilot in the SR-71 are to basically fly the aircraft. There are no controls to fly the aircraft from the rear cockpit. All the controls are in the front. When we are in flight, my primary responsibility is to keep the airplane going in a straight line, going on the fuel curve that we have planned and on the mission profile.
The officer in the rear seat is called the RSO, for Reconnaissance Systems Officer. He operates the specialized photographic equipment and other surveillance sensors carried in the special bays in the belly of the aircraft.
Yes, I back up the pilot most of the times. I'm running a checklist as a co-pilot, watching the fuels and the CG as a flight engineer. And then once we get up to airspeed and altitude, my role then becomes a sensor management. I monitor all the sensors, make sure everything's running well. If anything goes wrong at any time, I'll start backing up the pilot again. But once again, after that portion gets finished, we'll go back into a descent and I perform co-pilot and navigator functions.
Operating on the edge of space means the crew must wear specialized clothing. Before each flight, the pilot and RSO are suited up in an exercise reminiscent of space missions. These space suits are similar to those worn by the Mercury and Gemini astronauts. They were also used on the first shuttle missions. Piloting the SR-71 is a very demanding job. When flying in such difficult environment at such high speeds, the pilot must carefully watch every aspect of the plane's performance. There's no margin for error 80,000 feet over the Earth. Yet there has never been a shortage of volunteers for this duty. Crewing the SR-71 is viewed as a prestigious posting among airmen, and the Habu pilots are a very small and elite breed of aviators.
All things considered, the SR-71 is a very difficult airplane to fly, primarily because of the task overload that can occur if systems begin to fail. Generally, when everything is up and running, we are very busy. A 5 or 6 hour mission goes by very rapidly. Because of the speed that we travel, you have to stay well ahead of the aircraft from a pilot's standpoint and also from a reconnaissance systems officer's standpoint. We're covering over 32 miles a minute, and it's about a mile every 2 seconds, obviously, and at those speeds, when something goes wrong, you can rapidly deteriorate.
With the advent of the first satellites in the late 1950s, spy systems entered the uncharted environment of space. Photographic spy satellites orbit about 125 miles above the Earth's surface, nearly 10 times higher than spy planes like the SR-71 or U-2. The first space spy was the American Corona photographic satellite, also known by its cover name, Discoverer. Neither the CIA nor its Soviet counterpart released films or photos of their spy satellite, so for this program, we have recreated these highly classified spy machines using the best available data. The Corona satellite contained a high-resolution camera in its main compartment. Once its pictures were taken, the film was fed into a special compartment in the nose, and the nose cone ejected back to Earth. After it entered the Earth's atmosphere, a parachute opened to slow the photo capsule. To prevent the damage or loss of the capsule, it was intercepted in mid-air by a specially equipped aircraft with a unique hook system. In 1971, the Corona was followed by the KH-9, better known as the Big Bird. Corona only had a single film capsule to return to Earth, and its resolution was not adequate. Big Bird had at least 4 film capsules and could distinguish objects as small as 1 foot under good atmospheric conditions. In addition, it could electronically transmit images back to Earth without the need for the special film capsules. The Soviet Union soon followed the United States with its own photo satellites, beginning with the Cosmos 4 in April 1962. As in the case of the American spy satellites, the Soviet satellites evolved with improved capabilities, gradually becoming able to take photos with greater and greater resolution. But just how good is the quality of the images available from modern spy satellites?
The resolution of our photont satellites is not, contrary to popular opinion, good enough to read license plates on cars, nor to be able to distinguish between one mullah from another by the cut of his beard. That is not true. Resolution has reached its theoretical limit on a system like the KH-11, which is about 3.5 inches. But there are also atmospheric perturbations which change that. And even though they have ways of compensating for some of that, on the bird, as well as on the ground, with the way they manipulate the digital imagery, it is still not 3.5 inches. It is somewhere between 5 and 6. That is as good as it gets from an altitude of 125 or 130 miles shooting straight down. It's about a foot when you shoot from 500 miles. The imagery that we took of the Soviet aircraft carrier, which was in Janes, in July of '84, the obliques were taken from 504 miles, and looking at the picture, it might as well have been taken from a Cessna at 5 miles. I mean, you can see windows very clearly and all kinds of stuff on the deck of the carrier. I mean, they got an incredible intelligence yield from that kind of stuff. But it is not license plateville. No, it isn't.
Photo satellites were soon followed by radar surveillance satellites called RORSATs, or Radar Ocean Reconnaissance Satellite. A major problem with photographic satellites is that they cannot easily penetrate cloud cover. This is not a problem when surveying stationary objects like missile silos, which can be photographed some other day when the clouds are absent. But surveillance of moving objects like warships requires constant tracking in all weather. This led to the development of the first radar satellites, the RORSATs. The radars on these satellites cannot provide the precise images of photographic satellites, but they are able to keep track of fleet movements, no matter what the weather conditions. The next leap forward in photographic spy satellite technology came in 1976 with the launch of America's keyhole KH-11 satellite. The KH-11 could digitally transmit very high-resolution photos in real time. The intelligence agencies no longer had to wait for the return of a film capsule in order to obtain high-grade imagery. This was enormously useful in tracking the course of rapidly changing developments, such as the Iran-Iraq War or the war in Chad in the 1980s. In spite of the impressive performance of photographic satellites, there are limits to what they can see. Cloud cover is a constant problem, even when using sophisticated infrared film. The ocean surveillance RORSATs have very poor resolution when used over the ground. However, new developments in radar technology have made it possible to construct massive space-based radars that have very fine resolution, not substantially inferior to that possible with cameras. As a result, the superpowers now use real-time photographic satellites for certain tasks, supplementing them with radar imaging satellites when weather interferes with their missions. The combination of radar imaging satellites and real-time photographic satellites have enormously increased the operational capabilities of the space spies.
The changed capabilities in reconnaissance satellites, photo reconnaissance satellites, from 1960 when they started until now have been fundamental. Obviously, resolution has gotten better, but more important was the development of real-time capability. Indeed, there are two very important developments in terms of reconnaissance satellite capability. One is, as I said, real-time, which means that we can get information virtually as it occurs. As a matter of fact, in 1985, there was a party at CIA headquarters to celebrate the 25th anniversary of the first Discovery satellite, and then CIA Director William Casey showed photographs at 2:30 in the afternoon that had been taken over the Soviet Union 10:30 that morning, 4 hours later, which was a kind of cute touch to make the point that real-time was an extremely important development. The other is radar reconnaissance, which came into play with the advent of the satellite that used to be called La Crosse. Radar reconnaissance allows them to see through clouds and virtually any kind of weather. So between real-time imagery, delivering the stuff very quickly, Flash Gordon, if you want to, and the radar stuff, we've got quite a good capability.
Besides their use in collecting photos or radar images, satellites are widely used to gather many other forms of intelligence. Modern weapon systems emit many different types of electronic signals from their radars, radios, and other electronic systems. These signals can be picked up in space and then transmitted back to Earth for analysis by sophisticated computers.
The primary other system is called SIGINT, or Signals Intelligence, and what those satellites do is listen. Most of them are parked at geosynchronous orbit, which is 22,300 miles out, so they can stay over one spot on the Earth as it turns, and they essentially listen. They've got very, very powerful antennas, and we have got very powerful stuff on the ground that picks it up. So they listen, in the case of Rhyolite, to 11,000 telephone calls simultaneously. And then at the National Security Agency, they sort out, by using programmed code words in their computers, they sort out what they need. We also use so-called defense support system satellites, which are technically supposed to warn us of missile attack to follow missile tests, including air, ground, and sea-launched cruise missiles. They're also parked out at geosynchronous orbit, and we can watch virtually all their missile tests with those machines. We've got satellites that do radar work, measuring the kind of pulses their radars give off. So in the event of war, we know how to avoid them. So there are any number of such systems that are not photographic.
The sophisticated spy machine, whether a manned aircraft or a remote satellite, has become an essential tool in the conduct of national policy. Reliable intelligence collection has helped to reduce tension between the superpowers by removing suspicions about their military preparations.
There is no national security without them. They are now so pervasive and so important that it's unthinkable that there would be national security without them. They're used everywhere for a wide variety of things, and it's unimaginable that we wouldn't use them now.